Okay, so if so, let's start with a different topic. And this is a completely new part in the module. But it's a quite important part. And the reason why I bring this up now is because when I have master students, and especially projects, they have to do, very often they have to do two things. They have to do the communication side, and then they have to do the optimization side. And if you want to write research papers nowadays in communication, the optimization is always a very, very popular tool to actually design and optimize the system. Along with nowadays machine learning techniques and stuff like this as well. But for communication, optimization is actually quite powerful because it can really tells you when you can, under what circumstance you can find an optimal solution and under what circumstance you cannot. Right, so what we're going to look at here is optimization techniques for problems that are convex, and then I will explain you what convex means. And I will give you the fundamentals of convex optimization, but also I will tailor this as much as possible and as soon as possible towards communication so that you have concrete examples. You could take multiple courses on convex optimization, right? This is popular topics in applied mathematics. In the department, we have also convex optimization course, advanced optimization course that is given by control theory, control people in level 11. But it goes across essentially many fields. You can use optimization for different applications. So I'm looking at the time, yeah. So what we're going to look at, and we'll start really today, this afternoon, is look at mathematical optimization and look at why mathematical optimization is useful in the context of wireless communications. And then we'll look at all the different or popular methods of optimization that are used in communications. And you'll see there are quite many there. So I will skip this for the time being, but we'll come back to this whenever there is a question. So we have seen already, and I mentioned a few times, that if you have sum rate maximization, you can say, well, you have to maximize your sum rate, but then you have to find your precoder that maximizes your sum rate. Zero forcing was not optimal. If you have power location, you need to find the power location. If you do water filling, we have seen water filling, the insight, but this solution comes from a convex optimization problem. So there are numerous examples in communications where actually you need to formulate an optimization problem based on the communication theoretic foundations, and you have to marry optimization and communication theory principles in order to come up with very efficient system design. So what is a mathematical optimization problem is the following. Is typically you want to minimize, or it could be maximization, but we'll see in a moment maximization, minimization is just a minus essentially. So you minimize an objective function that we're going to denote as f naught of x, where x is the optimization variables, and is a vector, typically, could be a vector. So you can have, for instance, x could be your power locations across multiple antennas, multiple streams, for instance. You're going to have multiple entries in that vector. And this is your optimization objective function, and you may be subject to constraints. And so two types of constraints here. You have an inequality constraint and an equality constraint. And the dimension of x here, I will denote by n. And you can have m inequality constraints and p equality constraints. And we say that the x that is the solution of this problem is called globally optimum if you can find if this x is such that this objective function is always smaller than the objective function obtained for any other values of x within the domain that is defined by this constraint, right? So for all feasible x. So what that means by feasible x, it means that all the x that essentially satisfy those constraints, right? So this is global optimum. We say that x tilde here is locally optimum if it's essentially is better, if the objective function is better than for any other x, but just locally. So if I give you a very simple example, if you have a function like this, and I'm doing this just one-dimensional, I have a function that goes like this, right? So this point here, this x, would be, for instance, the global optimum. So for all values of x between here and here, that would be the one that leads to actually the smallest f naught, right? But this point here, for instance, could be, this x tilde could be a local optimum point. Local optimum because locally around this region here is actually better than any other point. This is local optimum, right? This is why we say locally means it satisfies the constraint, those constraints, but just such that it's, you know, in this boundary region for given epsilon, right? So this is an important distinction between local optimum and global optimum. And some optimization problem, we can solve them globally so that we can find a value so that the objective function is better than for any other x. And some other optimization problem, we can find them only a local solution, right? So it's interesting to know whether your solution is global or local. Right. By the way, anyone has done some optimization before? No? Never?
I've done things like methodology and machine learning on the data.
Okay.
To minimize the case.
Okay. Okay. So in general, so optimization problems can be very difficult to solve, but some problems are much easier to solve. And those problems are actually the convex optimization problems. So those ones nowadays, with modern techniques, they can be solved very efficiently, computationally, very efficiently, and also very reliably, because we can really say, okay, that's a global solution optimum. And they are characterized by convex optimization problem. The interesting thing is that you can, if you show that actually a problem is convex, you know that you can find the global solution, the global solutions. So that's why it's interesting to know whether a problem is convex or not. And for instance, the water filling solution is actually the global solution, global optimum solution to a particular convex optimization problem that is very relevant in communication. So what is a convex optimization problem? Is problems where the objective and the constraints are all convex. So what that means to be convex is to have this kind of relationship. So what that means is that if you take any 2 points, x and y, and you take a weighted sum of those 2 points, and you apply a certain function here, that could be your objective function or could be your constraints, you can say that this quantity will be always smaller than applying this function at each of those variable x and y and then weighting them afterwards. So what that means concretely, it means the following. If I have 2 points, for instance, x and y here, and I take a linear combination of those 2 points for any points in between here, for instance, this one, I have this point here, this a, I can say that this f of a here will be smaller than the value that is computed by weighted those 2 extreme points here. So in other words, the value of the function will be smaller than the chord. So the chord between those 2 extreme points here will be always higher than any points actually on that functions, right? So this is to give you a flavor. We'll see this this afternoon a bit more details. But you will see these examples. So it's quite intuitive. Convex means essentially you have some form of curvature, but to the top. And so you can show that it's convex if you take any points on this curve and say you draw the line, the chord, and this chord is always larger than any point that is in between here. Right? So for instance here, this one, I will have trouble. In this region, it will be convex. I take any 2 points here, this one will be actually lower than this chord. But if I take a point here and a point there, you see that sometimes it goes above the chord and sometimes it goes below the chord. So that will not be convex, right? But so if you can have this, this is very interesting because this is actually a quite general class of problems. And if you have an equality here, then you have a linear problems. And so linear relationship will always be a particular instance of a more general class of problems which are convex. So that's why I'm saying linear programs or linear program optimization are always part of this more general class. Okay, so for those who have done some optimization, the notion of linear programming is actually is quite old, and it's very well known in economics and econometrics and in some business schools, because lots of problems in those areas can be factors as linear programs. But in the past 20 years or so, there's been a lot of progress into generalizing the concept of linear programming into what is now known as convex optimization. Right, so let's look at this in a bit more details. And this is typically what people go through when they look at optimization in communications. And so this is what, you know, my PhD students Hongyu and Longfei and Meng who are there actually do on a daily basis, is essentially they first try to learn, you know, what's the state of the art in a certain field, right, in communication. And then you try to identify where you have a research gap, where actually you have something that is missing and where you want to push the boundaries. And those two steps are really the key. Is first you have to rely on strong communication theoretic background to say, okay, my communication strategy I want to look at is based on those principles, and those are actually the principles that we have talked about in part 1, 2, and 3. So if you do multi-user communication, you will formulate a problem based, for instance, on linear precoding, and where you actually formulate your SINR, your sum rate expression, and so on. And then you're actually stuck because you can face an optimization problem that says, well, now I want to maximize my sum rate in multi-user, multi-antenna communication, and I don't want to do precoding based on zero-forcing beamforming, for instance. Or I have a MIMO systems, but I want to find a better receiver architecture than doing zero-forcing receiver or MMSE receiver, but maybe have a lower complexity than something that is ML, right? So this is where actually optimization tools can play a big role. And I have to say that it's popular in academia. It's not so popular in industry so far, right? So if you look at a system like 5G or 6G, people don't really implement completely optimized solutions based on convex optimization, right? But it's something that optimization tools have evolved, and nowadays actually they're pretty efficient. So I'm pretty sure that one day they will be used in communication quite heavily. And then the last step is once you have formulated your communication theoretic problem and you have designed your algorithm to solve it, then you verify it, and obviously you have to show that you have better performance compared to the state of the art, right? So this is pretty simple, pretty common, I would say, and this is really what you do when you read the research papers. For instance, this is what you do, or if you have your master project or your final year project, your master thesis, right? You're going to have to go through something like this as well. Right. So those problems in communications, I said before, some of them are convex, some of them are non-convex, but very often they are non-convex and we don't know the optimal solutions. And so what we typically do is we don't know how to solve them, so what you try to do is you try to either convert them into a convex problem. So some of them, they look like non-convex, but actually by transforming the problem, you can find actually one formulation actually turns out to be convex. And so we'll see this later on today. Another approach is to say, well, the problem is non-convex, and so I will approximate it by some convex problems. And so in that case, you don't have maybe a solution to your original problem, but you may have a solution to a problem that is quite close to your original problem. Right? And one of the major challenge in those non-convex and convex optimization problem is how you can take a given formulation and transform it progressively such that actually the end formulation is actually convex. And it's not always possible to do, but we'll see some examples today where actually this is possible, and this is very powerful. Right, and sometimes you can have an original problem that is non-convex, and you may want to actually convert it into a series of sub-problems where each problem is convex. And by having that, you can actually also simplify the design of the system. Right, so let's look at this into a first application here. So we have our architectures that now you're a bit familiar with. You have this is essentially our multi-user MIMO architecture, the transmitter and the receiver. So this is what you do with the transmitter. You have K users that you schedule. So for instance, you have your 20 users that we had in the cell. And now we decide on a subset of those users that we're going to schedule at a given time instance. And you have the bits of information that you want to transmit to those different users. And you encode them using state-of-the-art error-correcting codes, and you encode them into K-independent stream, S1 to Sk. Right? So here your notation you will see in this example could be a bit different from what I use in the previous part, but it's essentially the same thing. So those could be, for instance, your QPSK streams or 16-QAM streams for each of those users, and then you linear precode them, and you transmit this over the air. So what you end up with essentially is this linear precoding here, where physically you have a transmitter, and this is the figure I had this morning, with multiple transmit antennas, and you have different receivers, and you create every time a different beams, where on each beams you have, let's say, S1, S2, S3, for those different receiver 1, 2, and 3. Okay? And so what you have there, once you have that, this is probably the simplest multi-user scenarios we have. You can say, well, I can now write my SINR for receiver 1, for receiver 2, or for receiver 3. So I can write my rate for user 1, user 2, user 3. And now I want to do a system design where I want to optimize those different beams or those precoders so that I maximize a certain objective functions. And these objective functions could be many different things. It could be, for instance, minimizing the total transmit power. So I want to guarantee, for instance, a certain quality of service at each of those receivers. For instance, I want to make sure that the SINR of each of those receivers is larger than a certain threshold, but I want to do this with the minimum possible transmit power. Right? So this would be one possible objective function, is then minimizing the total transmit power subject to a certain quality of service for those different users. Or you could say, I want to maximize the sum rate, and this is probably the most common, but unfortunately also very often difficult problems. Either maximize the sum rate or maximize the minimum rate. So in that case, I want to, for instance, maximize the rate of all those K users and potentially a weighted sum rate, so where I put different weights for different users depending on the priority. Or I want to, so that would be my maximizations over those precoders that we have there, over those W. Or I could have a maximization of the minimum over all K, of the minimum rate among those K users. Right? That could be a different problem. We have not really looked at this, and I've not really showed you that, but those could be completely two different problems. So this one typically, what you do there, if you relate to our rate regions that we had before, you have rate of user 1, rate of user 2, and then you may have maybe something like looks like that. So you have a given rate of user 1, a given rate of user 2, and what you do is that you try to move along this boundary region depending on the choice of your weight, right? And for a given weight, you actually try to maximize what's the best pair of rate of user 1 and user 2 in order to maximize this region. And so as you change your W, actually you change the points where you operate on this boundary, right? The minimum rate is something different. The minimum rate is trying to be extremely fair among all the users. So in that case, you want to find a point that is such that the rate of user 1 and the rate of user 2 are both maximized at the same time. So it would not be a point like this, for instance, where here you have lots for user 2, but very little for user 1, right? So those could be different points, and this point typically is always within your rate region or capacity region of your broadcast channel, but those refer to different implementation of the systems. And so some rate maximization, you really want to maximize the throughput in the network. Minimum rate, you want to maximize the fairness among all the users, right? Good. So those are the examples that we're going to look at today. Not today, actually today and a bit today and next week, not next week, in 3 weeks from now. But you see the different kind of problems. So you have transmit beamforming power minimization. So what does that mean? Again, this is this scenario where you want to have, you have precoders here, this is a precoder W1, W2, W3. And what you want to do is to minimize the power here in order to have a certain quality of service there. Or you could do MIMO detection. So MIMO detections is the case where we're going to have point-to-point system, right, at the transmitter like this, at the receiver, and we know that at the receiver we can do zero forcing, we can do MMSE, we can do SIC, we can do ML decoding, right? And the question is, can we formulate an optimization problem using convex optimization so that we end up with a way to actually do detection, but that would outperform some of those techniques and potentially have lower complexity than ML decoding, right? And then we have this kind of multicast case. So multicast, I mentioned this a little bit when we introduced multi-user communication. I said that you have unicast transmission and then you have multicast transmission. So unicast transmission is really when you transmit independent stream for all those different users. So user 1 here, receiver 1, will get a stream S1 whose data is completely independent from what is transmitted to user 2 and user 3, right? But you could have another scenario. So this could be the unicast, and this is really what we talked about so far. You have the multicast, which is, now I transmit from my multiple antennas. I still have maybe multiple of them at the transmitter, but now I want to transmit one symbol or one stream of information, X, but that is actually intended to all those receivers. So this is typically when you have broadcasting in the sense of, all people in the room want to watch the same football match, for instance, right? You have the same stream of information that is intended to all those different users, right? So there we're going to have a multicast beamforming where you try to do a power minimization, which means you try to, again, achieve a certain quality of service for all those receivers, but you minimize the power that is needed to do that. Or you can have the multicast beamforming when you do max-min fairness. So that's, you try to maximize the rate of each of those users, but you try to maximize the minimum rate. So you try to transmit these streams at the highest rate, but this rate has to be decodable by all those 3 users, right? So this is max-min fair. Then we're going to have reconfigurable intelligent surface. So maybe some of you have heard about this. This is actually going to be the topic also of your coursework 3. So intelligent surface is when you have a transmitter, you have a receiver, And so typically what we do and what we have been doing so far is that you have a channel H, and what you do, you adjust your transmitter and your receiver as a function of H, right? You adjust your transmit power, for instance, you adjust your precoding, you perform a certain receiver design, always based on H. Intelligent surface, what they aim at doing is to have within the propagation environment a lot of passive elements. So you can imagine those are kind of antennas, but they're completely passive, so they don't have active RF components. And any wave that you transmit to a receiver will actually bounce against those intelligent surfaces. And what you want to do is to be able to control those elements such that you can engineer or manipulate the propagation conditions. And so you could have, for instance, in the room here, you have all the walls are covered by intelligent surfaces. And so if you want to focus all the energy in one point in space, essentially the walls will act in an intelligent manner in order to focus the energy in that point in space, right? And so by doing this, you can view this as a form of smart repeater, but the challenge there is that you need to have some control behind in order to control the phase and the amplitude of all those elements that we have here. And this needs to be done jointly with any form of beamforming that you do at the transmitter. And so this is where we have also a lot of the optimization that comes into play. Another scenario is multi-cell. And so we looked at multi-cell this morning, right, the system model. But if you have transmitters, transmitter 1 and transmitter 2, and you have, let's say, a receiver 1 and receiver 2, and you have, let's say, single antenna at each of those nodes, and you can have many of them. The question is, well, I want to transmit to this user, but when I transmit to my respective users like this, I'm also creating interference to the other users, right? Something like this. And so what I want to do is to control the power at each of those transmitters in a dynamic manner in order to maximize my objective function. This is really power control. So either I do, for instance, on-off power control, I turn on all the transmitters, or actually I switch them off. But the problem is that you have this coupling. So you have this interference that is created. And so the interference that the power level that you choose here will be actually a function of how much interference that you create to others. And so you have to choose this power level across all those transmitters in a very efficient way. This is very common in this multi-cell. And then the most famous one that we have touched upon a little bit already is also a power allocation, but is this using this water filling. And so this is really the case where we had this scenario here, right? We had this transmitter and this receiver, and we had this channel matrix H, and we were doing an SVD of this, right? And then I was precoding using the right singular vector, combining using the left singular vector, and we were left with parallel channels. And the question was, how do we allocate the power across those parallel channels, right? And the solution was water filling. You could do this if you have an OFDM system. So if you have frequency domain transmission, you have a band like this, where divided into subcarriers, and on each of those subcarriers you transmit information, and those bands do not interfere with each other, so they act as also kind of parallel channels. And the question is, you have a total power budget for the whole band, and how do you allocate power across all those different subbands? So this would be the solution of a sum rate maximization subject to some power constraint, and this is the solution is the water filling. Right. Another application that we looked at a lot as well, and you can ask you, Meng, if you're interested in this, is the question of slightly different from communication, but you see that actually those techniques are applicable in many fields, is you have a transmitter, you have a receiver, and instead of communicating information between the transmitter and the receiver, what you want to do is that you want to use the radio waves to power up the receiver. So you want to do power transfer, but in a radiative way. So you use the electromagnetic wave to power up, for instance, low power sensors, right? And there the question is, how do you design the signals at the transmitter or the waveforms in order to maximize the amount of energy that you can deliver at the receiver? And so this is also the solution of an optimization problem, and we'll see some illustration of that. So far, all those techniques, all those applications actually use different type of problem formulation and optimization solutions. And then transmit beamforming with rate maximization, that's getting a little bit more complicated. It's this problem here, but instead of minimizing the transmit power, we try to maximize the rate at those different users. And so it could be some rate maximization or maximum rate maximization. And then you can have some receive beamforming as well. Right, so this is the techniques we're going to look at. First, some basics concept, and then we'll go into all those fancy names here. Linear programming, QC, QP, SOC, PSD, PSDR, GP, and KKT. And for each of them, the idea is not to go into all the details of this. You have a reference book for that if you're interested, but that could take you the whole year to study. Is instead having key idea of what is each of those problems and how do you map this to actually a communication problem. And this is often the challenge with students, is that you have, on one hand, you have communication courses, on the other hand, you have optimization course, and then the link and the map between the two is actually quite difficult. Okay, so any questions so far? Then we're going to start this. So let's look at first the notion of convex sets. So to understand a convex optimization problem, you need to understand the notion of convex set and convex function. So what is a convex set? It's something that is very easy to imagine, qualitatively. So a convex set is, or a set is convex if you take a line segment between any 2 points in this set, and so a line segment would be written typically by this. You have a point X in a set, you have another point Y in the set, and actually by taking the line segment here, you take all points between X and Y on the lines between X and Y by adjusting theta. So for theta taking between 0 and 1, you actually going to take any points from X all the way to Y. And this set is convex if for any 2 points X and Y, the line between those 2 points is also in the set. Right? So an example is the following one. If I take a point here and a point there, if I draw the line between those two, right, this line or this segment will still be within this set. In this case, it's not convex because if I take a point here and a point there, the line would be within the set, but I can take a point here and a point there, and if I draw the line segment between those 2 points, you see it goes through an area that is not within the set. So this set would not be convex. And this one here is not convex either because on the boundary, you have some elements here, some points actually are within the set, but then you have some points here are not within the set. So if I take a point here and a point there like this, it's okay. But if I take the 2 points here on those 2 edges, well, and I draw the line, the boundary of the square would not be within the set. So this would be an example where actually this is not convex, this is non-convex, but this would be convex. And you can have many examples like this. So if you take a unit ball, for instance, so unit ball is really a complete, imagine you have a basketball, for instance. So you take all vectors x, such that the norm of x, second, for instance, L2 norm, so second norm is smaller than 1. So you take all the points within, for instance, your basketball, right? And so you take any 2 points, and the line segment will always be within that ball. But a sphere would not be convex because the sphere you operate on essentially the boundary of the ball, and so if you take 2 points on this boundary, essentially all the middle points do not belong to that set. Right, so if you're interested, this is the reference book for this part. This is actually quite long book, so I think it's probably 800 pages long. It's much more detailed than what we're going to cover. But a lot of what I cover here, or what I cover here on the theoretical part really comes from chapter 1 to 5 of that book. And then going to have reference to more communication principle as well, or optimization for communications. Right, another interesting property of convex sets is that if you take the intersections of any number of convex sets, well, this intersection is convex. So this is quite a nice property. It says if you know that a set A is convex and a set B is convex, well, the intersection between those two will still be convex, right? And so this is an example here that actually is very helpful. This is a polyhedron, which is an intersection between half spaces. So a half space here is determined by this relationship. You take all the vector x such that essentially you're on one side of the linear relationship ax is equal to b. So ax is equal to b could be, for instance, this line here. And so on one side, you're going to have ax smaller than b, could be this side, for instance. And on the other side, you're going to have ax is larger than b, right? So this is your essentially half space. You're looking at half of the space defined by this relationship. And if you have a half space, you're going to have convex, because any points on the left side of this line will be actually a convex set. And now you actually take the intersection between multiple of those half space, you're going to still have something that is convex, right? So this is quite interesting, because we'll see that a convex problem, if you have convex inequalities and you have multiple convex inequality, well, the intersections of those multiple convex inequality will actually be a convex set. Right? So this is quite useful. Right. Another interesting concept is the concept of cones. And so a cone is a very specific type of set that says the following. A cone is actually convex. A set is convex. A set is a cone, when you have the following relationship. So you take a given x in a cone K. If any scaling, positive scaling of that x is still in the cone K. So for instance here, if I take 2 points x1 and x2, and I scale x1 and x2 by any positive value, those scaled value of x1 and x2 would still have to be within that set. And it's convex because you have a linear combination of any of those 2 points would still be in that set. So the line segment between any of those 2 points, a scale version of x1, a scale version of x2, and any line segments between those 2 points are going to have to be within that set. Right? So this is what is called a cone. And it has to be essentially, it's infinite here in one dimension, because your values of theta 1 and theta 2 are always positive and could be all the way to infinity. So one particular, so this is maybe a pi slice. You can imagine pi slice going all the way to infinity. Another example is this one, which is this non-negative orthon, which is a complicated name for something that is just something that everybody knows. So you're looking at this area. So you're looking at x1 and x2, and you're looking at all the values of x1 and x2 where x1 and x2 are positive. Right? That's what it means. Right? So this is in a two-dimensional case, and you can define this into the n-dimensional case. Right? So this is, again, this is a convex cone, because you take any 2 points here, right? You take a scaled version of those 2 points by gamma theta 1, theta 2, and any line segment between those two will actually still be in that cone. Then maybe the most well-known one of those cones is called second-order cones, and you can view this as a form of an ice cream cone. It tells, well, if you take the L2 norms of a vector x, you're looking at all the points x, so a dimension n, so this is a vector n, and all the values of t, that is a scalar, positive scalar, such that the L2 norm of x is smaller than t. And so if you imagine x is a two-dimensional vector, and you have t is a positive scalar, so what does that represent? It represents this ice cream cone. For a given value of t, let's say t is equal to 0.5, you take all the values of x such that the L2 norm of x is smaller than 0.5. And as you increase t, essentially, you enlarge this cone because you have more pairs of x1 and x2 values such that the L2 norm will be smaller than t. Right? So it really looks like an ice cream cone. And again, it's a convex cone because you take any 2 points within that cone, you scale by any positive values, and you take the line segment between any of those 2 points would still be within the cone. Right. Another way to see this, which is also useful, and that relates to what I said earlier on, is that if you have here a certain number of half spaces, right, and you take the intersections, here you're going to have a convex, the intersection of convex set is still convex. Now imagine that you take those half spaces, but you take an infinite number of them, and you wrap them around that cone. So each of those facets here is obtained by essentially a half space, and you have an infinite number of them. And so the intersection between all those half spaces will actually create this cone. And since we said that the intersections of convex sets are convex, essentially the intersection of all those half space here would create the convex cone, right? In this case, the second order cone. Right. One more definition of cone or type of cone is this positive semi-definite cone, which plays with positive semi-definite matrices. And so this is a type of matrix that we have seen already quite a bit, even though I did not mention. But when we played with covariance matrix, for instance, the input covariance matrix that we were optimizing in the capacity of a MIMO channels, or the covariance matrix of the channel, for instance, right? So those are typically examples of matrices that are positive semi-definite. So what that means is that the matrix is positive semi-definite, and I take the matrix M, for instance, and we have either we write PSD or we write with this curly notation. So a matrix is PSD if you take any vector x here, we operate in the real field, so of dimension n, such that x multiplied by m multiplied by x essentially is larger than 1, right? So this would be a scalar quantity, right? So you have a column vector, this would be a row vector multiplied by this PSD, and for any x, this quantity is always positive. So that's the definition of a PSD matrix. And what it equivalently, you can say M will satisfy this property if M is symmetric and if all its eigenvalues are non-negative. And this is really what we have when you look at input covariance matrix in the MIMO system. For instance, this is a PSD matrix where you have maybe some eigenvectors and you have the eigenvalues, and the eigenvalues represent the power location, right? Typically, they cannot be negative. They're either 0 or they're positive, right? And same for the covariance matrix of the channel. The covariance matrix, you can have eigenvectors, and you're going to have eigenvalues that will depend on, the propagation conditions. but they will never be negative. They will be always equal to 0 or positive. So those are two typical examples that we have in communication of PSD matrix. And another one that we'll see quite a bit is if you take a vector channel H, right, and you multiply by its Hermitian, right? You could say, well, this is still a PSD matrix because I have a vertical vectors and I multiply by a horizontal. So this matrix will have one non-zero eigenvalues. All the other eigenvalues will be 0, but it's still a positive semi-definite because all its eigenvalues are non-negative. Right? Right. So the set of PSD matrices is given by this. So this is all the set of matrices X that are symmetrics, but such that X is PSD. And this set of all those PSD matrices is actually forms a convex cone. So how can you show this? You can show using this relationship. So you have to show that if you take any matrix, any PSD matrix, and you scale them, and you take a linear combination of those two. So I'm just taking the definition here of cone that we had here, right? Instead of having an X, now I'm taking those matrices, those PSD matrices, and I'm saying that if you scale them and you combine them, this quantity will still be positive semi-definite. And so how can you show this? You say, well, if I take this combination, if this is positive semi-definite, I can multiply by X, I can multiply by X, I can distribute, I have two terms, and because A is PSD, this term will be positive, because B is PSD, this term will be positive, so this quantity is positive, and so indeed this is a PSD matrix, right? So all sets of, so this is essentially a convex cone because you can take any two of those A and B PSD matrices, you can scale them like this, you will still be within this convex cones of PSD matrices. Right, so this was for convex set in, I don't know, 15 minutes or so. If you want to know more, you can look at these reference books. There's probably a whole chapter, right, on convex set that will take you into much more detail. But I think this is really the fundamental that you need at this stage. Convex function. So what is a convex function? And I gave you already a flavor of this at the beginning. But imagine you have an n-dimensional vector here, and you have a function of this n-dimensional vector. And we say that this function is convex if you take any of those possible values of argument of this function, and you're looking at the line segment between any of those 2 points. So this would be given by this quantity, and the value of that function at any points on the line segment between x and y should be smaller than its chord. So what that means is the following. You have a point x here, you have a point y, you take any points in between x and y, its corresponding output, so f of this corresponding output will be here. For any value of theta, the value of the function will be smaller than its chord. Right? So this is a visual representation of what that means. F of x is here, f of y is there, and this is essentially the chord that links those two points. Right? And so if you have a function that has the opposite behavior, that is something like this, right, is concave, well, essentially is the opposite. A function is concave if it's minus that function is convex, right? So it's easy to remember convex and concave, what it means. Concave, you think about a cave. A cave is like this. So concave means the curvature has to be like this, right? So that's the easy way to remember this, right? Convex is the opposite. Okay, so this is the basic definition of a convex function. And actually, this holds whatever function you have. So the function does not have to be differentiable or something like this. It's a general definition. Right, so let me show you a few examples of convex function. And for some of them, you can show them using the definition. For some of them, we can show this using other properties of convexity. I will show you this in a minute. But let's imagine that I start with this function absolute value of x, right? So if you have absolute value of x, this is your x, and the absolute value of x will be something like this, right? So there, this is a convex function. It's not differentiable, right? At this point, it's not differentiable, but it's convex because you take any 2 points here and you type you draw the line segment. It will be above that values, right? So this is a convex function, exponential of ax for any a in the real field, right? This will be convex as well, right? Exponential is something that goes like this. So you take any 2 points here and there, and you're going to have a line segment here that will be above the function itself, right? X squared, right? You know what x squared looks like. You have something like this, right? So this is also convex. X log x is convex over r plus, right? So r plus means you take all the real values from 0 all the way to infinity, so non-negative values. And this one, you can show this is convex using some other properties we'll see in a minute. And then you can have the opposite. Concave, for instance, is square root of x. So that looks like something like this, right? So you see you have a curvature that is the opposite. In this case, you take your chords. The chords will actually be lower than your function. Right? Log x as well is concave and so on. And then you have affine function. So affine function is a function that is here is linear. So this is the linear terms. And then you have a constant. This is what is called affine. So essentially, it's the same as linear, but in math there is a slight difference. It's a linear function that has to pass by 0. So affine means it's linear plus a constant. But this is essentially a straight line, and a straight line is convex and concave, right? So it has both properties. X cubed, for instance, is convex in the positive for positive x and concave for negative, right? Because you have something that looks like this, right? So you have a convexity here on this side and concavity on the other side. And then you have a norm, and the norm here you have a p norm. So this is just as a reminder, the p norm, you take a vector x dimensional n, you take the sum of the entries to the power p, and then you take 1 over, not the square root, but 1 over p, I don't know how do we call this, to the power 1 over p, yeah, right, for p positive, and you can take any value of p. This will be your p norm, and this is always convex. And how can you show this? Well, you take any 2x, any 2 point x, n dimensional, you take this linear segment between those two, and you have to show that actually this would be smaller than the chord that is obtained as follows. So if you take the triangle inequality of norms, it says the sum of those two quantities is essentially smaller than applying the p norm on each of those components. So this is a property of norm. All norms, all p norms for any value of p have to satisfy this relationship. This is called triangle inequality. And then you have the homogeneity property of the norm that says if you scale your vector x by a given theta, you can actually take the theta and bring it outside. And so what you end up with is the typical relationship that we had. This is your function of x, right? This is your function of y, and so this is your chord that is obtained between f of x and f of y, and this is higher than actually your function that evaluates any points in between x and y, right? So this is by using those two properties, you show the convexity of the P norm. Right. So how can we show that a function is convex? Well, the first one is by applying this property. The second one, that is the second property of convex function, if your function is differentiable, is to say, well, being convex is equivalent to saying my function at any point y will always be here, the function at any point y will always be larger than the first order Taylor expansion on any point x. So I can take any point y here, and I can take the Taylor expansion here on any of those points, and this Taylor expansion will always be an underestimator of this function, right? So this is another way of another property of convex function, and because you use the first order differentiability, you have to assume that f is differentiable. So this is a condition that holds when you have f if is differentiable. Right, and what is interesting is the following. If your function is convex, then you know that this first Taylor expansion will be an underestimator of the function, but you can show the opposite as well. If you can show that this one is always underestimator of that function, then you can show that actually that function is convex. So it goes into two directions. Convex function implies the underestimator, and if you say that actually you have an underestimator of that function, then you can show that that function is convex. So it's if and only if you like. It goes in both directions. Right, and so another property of convex function, if you look at second order condition, and this is something you're familiar with based on just high school math, is saying you're looking at the curvature, right? And so in this case here, right, what is the curvature of this? If you take the second order derivative of this curvature will be negative. If you take something like this, and the curvature is positive, you say, well, this looks like this, so this will be convex. That's the idea. Here, if you have a function that is twice differentiable, and you can show that for dimension 1, your second order derivative is positive for all values of x, essentially you have a convex function. In general, if you don't have only dimension 1, but you have a vector of dimension n, then you have to look at the Hessian of that function. So you look at the second order derivative of this function with respect to all quantities. So for instance, if you have dimension 2, for instance, you will look at your second order derivative with respect to x. So let's say you have f is a function of x and y. You have df dx dy, you have dy dx, and then you have dy, right? Right, so this would be your essentially Hessian, and you have to show that this, with all the entries in your vectors, if it's n-dimensional, you have n by n matrix, and this Hessian has to be positive semi-definite, so PSD. Right, and so case where this is useful, take two examples here, is when you have a function f that is quadratic. So quadratic here has this typical behavior. You have here these linear terms, and here you have these quadratic terms where you have this x multiplied by x. So this will give you, for dimension 1, you're going to have an x squared essentially, right? And your p here Well, your P is your symmetric, typically a symmetric matrix. And if this matrix is positive semi-definite, if P is a PSD, then this function f will actually be convex, right? And so how can you show that? Is if you take the second order derivative of f, if you take a first order, you're going to get rid of x here, you're going to get rid of x. If you take second order, all this term will be gone, and you're going to be left with getting rid of x here, getting rid of x there, and you're going to be left with p. So that's going to be your second order derivative, or your Hessian of f will be p. And if p is now semi-definite positive, then the Hessian will be positive, so PSD, positive semi-definite, right? And so in that case, this function will essentially be convex if P is a PSD matrix, right? And this is something we'll see quite a bit in communication, and I will show you some examples. Another example is this one. So this is quadratic over linear. I have two inputs, so n is equal to 2 here. Two values in my vector x, and is given by x squared divided by y, and we say y is positive. And so if I take the Hessian of that function, so I compute this quantity here, right? You can do this at home. You get this relationship. And so what you see here is that you see that the function to be convex here, it has to be convex in each of those variables. That's important, and we see this here. For y positive, this is the second order derivative with respect to x. This would be the second order derivative with respect to y. And those two quantities are always positive. So that means actually, indeed, the function is convex in each of their variables, right? But this is not sufficient. Is there someone waiting? Hi. So your second order derivative is positive with respect to the first entry and the second entry. So this is needed to be convex, but this is not sufficient. Your function here, your Hessian is PSD, not only if you have this is positive and this is positive, but you need to look at the diagonal entries of that matrix as well. And so in this case, in this particular example, this matrix can be written as the product of two vectors. So this matrix will be rank 1. So it will have a 0 eigenvalue, and it will have a non-zero eigenvalues. And this will be positive, right? So one thing that is important, and you will see this, I think, in coursework 3 as well, is that if you have a convex function, it will be convex in each of those, in each variables, right? So if you have a function that is function f with over domain of size n, Rn, the function will have to be convex in each of those n variables, x1 to xn. But the opposite is not true. So you could have a function that is convex in each of the variables, but is not globally convex. So its Hessian is not PSD. And there are other examples. So for instance, the log sum exp, so which is the log of the sum of exponential. This is convex as well. This is a bit more complicated to show, but you can also compute the Hessian of f and show that actually the Hessian is positive semi-definite.